Okay, as we continue, we have here a figure showing the consolidation characteristic of normally consolidated clay of low to medium sensitivity. So we have here, we try to graph our pressure and our versus the void ratio. So for what can be shown on this figure are the virgin consolidation curve, the slope C sub C, we have the consolidation curve for remodeled specimen, and we have laboratory consolidation curve. So for normally consolidated clays that exhibit a linear E-log of sigma prime relationship, we have delta E, which is equal to this expression. And you have to take note that C sub C is the slope of the E-log sigma prime plot, and this is defined as the compression index. So basically for normally consolidated clay, we have here the formula to compute for the settlement. So we have here figure 11.18. This shows the consolidation characteristic of over-consolidated clay of low to medium sensitivity. So for this one, in over-consolidated clay, wherein our sigma prime O plus delta sigma prime is less than or equal to sigma sub C, field E-log of sigma prime variation will be along the line HJ, the slope of which will be approximately equal to that for the laboratory rebound curve. The slope of the rebound curve C sub S is referred to as the swell index. So for this one, we have delta E, which is given by this expression, and to compute for our settlement, we have this expression. However, if sigmas of prime O plus delta sigma prime is greater than sigma sub C, then our expression will, to compute for the settlement for over-consolidated clay, is given by this expression. So we have here correlation for compression index C sub C. So the compression index for the calculation of field settlement cost by consolidation can be determined by graphic construction after one obtains the laboratory test result for void ratio and pressure. Skempton suggested the following empirical expression for the compression index of undisturbed clay. So we have here C sub C for the compression index, which is equal to this equation. And you have to take note that L sub L is the liquid limit. So for several other correlations for the compression index are also available. They have been developed by tests on various clays. Some of these correlations are given in table 11.6. So on the basis of observation on several natural clay, Rendon Herrero gave the relationship for the compression index, which is in this form. So this is to compute for the compression index with having a value of specific gravity and the initial void ratio. So Nagaraj and Morte, for the compression index, he has given this formula. And based on Roth and Wood, he has introduced this equation. And in the average value of G sub S is taken to be 2.5, Kolhawi and Main, he introduced compression index to be approximately P sub I all over 74. Park and Komoto express the compression index by this equation, wherein our N sub O is the in situ porosity of soil. So we have here tabulation showing the correlations of compression index C sub C. Given an equation, we have the reference and of course the region of applicability. So correlations of swell index. So the swell index is appreciably smaller in magnitude than the compression index and generally can be determined from laboratory tests. So our compression swell index is given by 1 over 5 to 1 over 10 of the compression index. According to Nagaraj and Morty, swell index is given by this expression. And Kolhawi and May, they introduced this based on the modified Camp-Clay model. They introduced this formula for the swell index. So we have here a sample problem. So for this one, we're going to have your you have the result of the laboratory consolidation test for the loading and unloading. So you're going to draw the graph of E log sigma sub prime O and determine the preconsolidation pressure. Then you have to calculate the compression index and the ratio of C sub S all over C sub C. Then, on the basis of the average E log of sigma prime plot, calculate the void ratio at sigma sub A equal to 1000 kN per meter squared. So we have plotted now our pressure versus void ratio. This plot was based on this equation, this illustration. This one, how to plot the pressure versus the void ratio based on Casagrande. You just follow this procedure. And following that procedure, we have plotted our pressure and the void ratio for this equation, and we have now this plot. And of course, the purpose of this is to determine our preconsolidation pressure. And on the intersection of this, because you're going to draw the horizontal line, you draw the line AC and you draw a midpoint between AB and AC, then you draw a tangent line to this. The intersection between AD and the tangent line that you draw is your preconsolidation pressure. So for this one, it was obtained that this is 120 kN per meter squared. Then, of course, you're going from the plot of that figure. For the loading and unloading branches, you can have this value. For the loading and unloading, when void ratio is 0.8 and 0.7, we have our pressure 200 and 400. For the unloading, which is 0.544 and 0.532, we got 200 and 400. That is based on this figure. So this one is the loading, and this one, so you have 200 and 400. For the unloading, you have this value 200, and the other one is this one, which has 400. So for the loading branch, your compression index given by this equation, you simply have to substitute the value for void ratio, and that gives us 0.33. For the unloading branch, you have this equation, and it gives us the value for 0.04. And the ratio between swell index and compression index, that is 0.04 and 0.33, so that gives us 0.12. So this one is your compression swell index. This is your compression index, 0.33. Swell index is 0.04. So this one, you have now your compression index. So using that equation. So basically, if you're going to substitute the value for E1, 0.8, and your sigma 1 is 200, sigma sub C is 0.33, so sigma sub 3 is 1000. So you simply have to substitute to our equation for this one, and you get the value for E sub 3, which is 0.57. Then for our sample number 2, a soil profile is shown in figure 11.21. So the uniformly distributed load delta sigma is applied at the ground surface. What is the settlement of the clay layer caused by primary consolidation? If the clay is normally consolidated, second, preconsolidation pressure sigma sub C prime is 200 kN per meter squared. And let us see your preconsolidation is 150 kN per meter squared. Of course, swell index is approximately 1/5 of the compression index. So for this one, so this is the given figure. You have 2 meters above the water table, then 4 meters below the water table, and 3.5 meters below the water table, and this is now a clay type soil. This one is a sand type soil. So for our first solution, we're going to determine the average effective stress at the middle of the clay layer. So the average would be equivalent to 2 times 14, the unit weight, then plus 4 times, this is saturated, so times 18 minus 9.81, the unit weight of the water, then plus, this since we're after with the middle portion, so 3.5 all over 2 times 19 minus the 9.81. So that gives 76.08 kilonewton per meter squared. And you can use this equation to substitute to get the value for the settlement. Using this equation, substitute the given values First, we have to identify our C sub C, which is equivalent to this. Substitute your liquid limit, then that gives us 0.27. So therefore, our settlement is equal to 191 millimeters. So part B, when delta prime O plus delta sigma sub prime O plus delta sigma prime is equal to, you simply have to add your computed average value for the effective stress, 76.08, your delta sigma prime, that is the surcharge additional load, which is 100 kilonewton per meter squared, so gives us 176.08 kilonewton per meter squared. And sigma sub prime C now is equivalent to 200 kilonewton per meter squared. So since our sigma prime plus delta sigma prime is less than sigma sub C, so we can going to use this equation. So simply have to substitute our parameters. So our C sub S, of course, is 1.5 of the compression index, which gives us 0.054. And using this equation, substitute now the parameters, it gives us settlement is 38 millimeters. For the letter C, we're given with sigma sub O, which is 176. We're given with sigma sub C, which is 150 kilonewton per meter squared, and we have computed now our sigma sub O prime, which is 76.08 kilonewton per meter squared, and this one is equal, we have computed this, which is equal to 176.08 kilonewton per meter squared. And if we try to compare, our sigma sub C prime is greater than sigma sub O prime, but less than sigma sub O prime plus delta sigma prime. So we're going to use this equation. So using this equation, this is now for over-consolidated clay. You simply have to substitute C sub S, swell index, our compression index, our vertical effective stress, our change in the stress, our pre-consolidation stress, your void ratio, and our H, which is the height of our soil in question. So H here is 3.5 actually. Simply have to substitute all those parameter values. Our settlement now is equal to 67.5 millimeters. So that is for example number 2. Now we move on to secondary consolidation settlement. Basically, when we talk about secondary consolidation settlement, this occurs after the completion of the primary consolidation settlement. Because when we talk about primary consolidation, of course, it was defined as the process in which the soil volume decreases. And it is also defined as the decrease in water content of saturated soil that happens without the replacement of water by air. So that is the definition for primary consolidation. Basically, when secondary settlement occurs, when the primary consolidation was done, was already completed. So I'm meaning to say that some settlement happens in the soil after primary consolidation, and that is termed as secondary compression, and it is usually time dependent. So in sandy soil, this type of settlement is negligible. It is different from the primary consolidation settlement, and it takes place at a constant effective stress. So meaning to say, the secondary consolidation settlement is shown after it occurs after the end of the primary consolidation, after complete dissipation of the pore water pressure. Some settlement is observed because of the plastic adjustment of soil fabric. This stage of consolidation is called secondary consolidation. During secondary consolidation, the plot of the formation against the lag of time is practically linear. The variation of the void ratio E with time t for a given load increment will be similar to that as shown in the figure 11.8. So this variation is shown in figure 11.23, and from the figure 11.23, the secondary compression index can be defined as you're given with this expression. This one is secondary compression index, change in void ratio over your time, T sub 20 sub 1. So we get now your secondary compression index.